Who's very comfortable with event loops? Okay, you're...
Sorry, I buzzed in too early.
Who?
I've used AnyEvent.
You've used AnyEvent, okay. So I'm gonna spend the first couple minutes talking about how event loops work generally, if that's okay. I'm giving a full presentation on event loops tomorrow. If what we do today isn't, you don't feel like quite solid on that. Tomorrow's is a general. It's not a Perl specific thing. We'll be talking about Node, the JavaScript event loops in browsers, Tornado, Twisted, some of the Python ones, some of the Perl ones. There's a lot out there. So just as a general concept of event loop. Okay, so AnyEvent in general is it's kind of like the DBI of event loop interfaces. It integrates very nicely with almost every event loop I've ever used it with, which is probably about close to 10 at this point. There's one that I used recently last year that it did not work with, but it wasn't because of AnyEvent. It was because the event loop didn't offer up any kinds of accesses into its loop for outside things. So we'll be talking today about AnyEvent, of course, and some of the low-level primitives on which you might build other useful tools. So let's see. Event loops. An event loop is a framework that allows for asynchronous programming. With an event loop, you tell the event loop what kind of things you're interested in, and then you give it some code to run when that interesting thing happens. It's a lot more declarative than imperative, if you know the two paradigms. Because you don't know when it might run, you don't know how it might get there. You just know that at some point in the future, something that I'm interested in is going to happen, and I want this code to run when that happens. So if you're familiar with Unix system programming, maybe you've used signal handlers. Anyone written a signal handler before, like a SIGTERM or SIGHUP? So a signal handler looks. I should have done that one. A signal handler looks like. Let me see if I can get the.
Like El Capitan?
It looks like El Capitan. There we go.
What's that? I don't know.
Not big enough for everybody. Can you see that? Okay. So a let's see. Okay. So a signal handler might be something like this, where we would say sig term sub this would be our signal handler. Actually, it should probably be. And then we would do something like, and something's going on here in the loop, and so we would then run this. Oh, what I need to do first is print my PID so I know what I'm doing here. Oops, I don't want to do that. Oops. Okay, so that's the PID. Kill. It's hard to look backward and type. I didn't realize how hard that was. I thought all these people are idiots, the other presentations I was doing. So we'll send a term signal to this process. And when we do that, watch this other screen carefully here. Actually, I'm going to, now that I've split the screen, I'm going to try this again. 33590. Okay, so we got our by at test line 4. So what's going on there? Well, what's going on is that what we've done here with our sig term is we've registered with the operating system our interest in this signal. It's an operating system signal. inside of Unix is an event loop, and it's running all the time, handling your things, and it can handle out of band events like keystrokes and signals that might map to keystrokes and timers and things. It's all built into the OS. Perl offers you a simple interface into that event loop of the operating system. So while we're sitting in our while loop sleeping, the operating system is still watching for signals and things like that. And in this case, it happened, and it said, the operating system says, oh, does anybody want to know about this signal? It sees our handler sitting there and says, oh, I better just fire this off, and away it goes. And so that's primitive event loop handling right there. So, sorry, my notes are on my phone here. So that's a basic operating system event loop. Your favorite web browser is a big event loop. When you have a little, when you make a jQuery call like .get, $.get, and you give it a URL and then maybe some kind of a callback in there, that callback, fires eventually. It doesn't fire right then. Your code just keeps on marching on, and eventually that callback will fire. That's because your browser is running an event loop. Let's see. So when you write an event loop, oh, this is a cool one. Let me see if I can make this work. There's my mouse. Sorry, I thought I had this one ready. Okay. Oops, which way? There we go. Okay, this is an example of why it's important to avoid blocking code in an event loop. This will just take a second. Hopefully this works. Okay, so well, let's see if we can pick one that doesn't suck here. WebGL, shader 2. Okay, so this is all running inside of an event loop. There's some code that's running, and it says every time we get every time the clock goes around a tick, we're going to reanimate the screen, and they've probably got 4 objects in there, and each of them has its own independent animation routines. If we go in here and we open up the JavaScript console, and we type in alert, hi, everything stops. What we've done, the alert dialog stops the event loop cold. Nothing else runs because it has to wait for input. If you're writing user interfaces, you typically want to use the non-native dialog that would be still let the event loop flow. This is useful maybe in debugging, but this is why it's important that you don't stop your event loop. It just kind of kills everything that you were trying to, the reasons that you went with your event loop in the first place.
That was funny. That was called free, and there were 4 boxes.
Yeah, that was the library, the name of the library. Yeah, I should have picked a different one, I guess. Perl has at least I would, well, it's 8 or 9 really, well, maybe half a dozen good event loops that were really well thought out. Some of the older ones would be event.pm. Some are interfaces into the C libraries like libev or libuv, wrappers around those, or libevent. Some of them are 100% pure Perl, like PO or IO async, and all of these have their benefits and their ecosystems. AnyEvent works with all of them. It can integrate with any of those and work just fine. You can swap them out, and if I have time, we'll get to an example where we do that. So the problem I find with AnyEvent is I've been working with AnyEvent for probably 5-6 years, and it was really hard for me. I think it was the condition variables, and I didn't understand how event loops work, so that's why I'm giving this little intro into event loops, having at least a basic idea of things don't happen in the order that you want them to. You got to give that up. You've got to just declare your handlers and let them fire. Please.
I mean, if we saw this with our event, our state engine, is most programmers do not understand that you have to do things differently with an evented system. You push things out. There is no, okay, this will happen and then this. You need to notify everyone, when the conditions are met that you can run. If you try and assume anything is going to be done by the time something else does, it will blow up.
Yeah.
And a lot of people don't. Yeah.
It's a different way of thinking about it for sure. Yeah. Okay. So one of the common ways to approach any event is with some examples. So we'll do that now. We've got a non-blocking web crawler. So let me get this one out of the way. Oops. Bring this other one back.
You can start a team-up session and attach to it from both screens.
Oh, I think that would take me longer to learn how to do than. Is that too cut off, or is it okay?
It's okay.
I can.
It's a little small, but it's okay.
I can. Is that better?
Yeah.
Okay. Oh, this isn't the one I wanted. There we go. Okay, so here we have a little. This is a web crawler. This is the Google search. Oops. I didn't actually steal this from Google, but this is what Google would have written if they were cooler. It goes out, and we make a little user agent. This could be LWP. Actually, it cannot be LWP because LWP doesn't do non-blocking I/O. But that's beside the point. This is a non-blocking user agent. There are a handful of those out on the CPAN. We give it a timeout of 2 seconds. We open up a little file that contains our URLs. It's a list of URLs. This will be our seed URLs. We pull those into the sites array, and then I want to see how much time this is going to take. So I start a timer, and then I run the crawl routine. Here's the crawl routine here. And after the crawl routine runs, I print out how much time it took. The crawl routine takes that user agent and then iterates over the list of sites. Each one of those is a link. We chomp the new line off of it. This is some of my debugging garbage that's still there. Then I print out the phrase fetching link. I start a timer. Then I do a web get. This actually could be done in LWP user agent because we're doing the blocking for him here. We do a web fetch, which means the program's running and it goes, and it goes and makes out a web request. And then I don't know how long that's going to take, but we wait for it. It comes back, and then we print out how long that took. We do that in a loop. So let's run this. This is fairly simple. Perl crawl blocking. Okay. Whoop. That was fast. Now why? Oh, I wonder if I don't have network. Hang on. Let me.
Were there any? Is it possible your sites exceeded?
Oh, yes, that is also very possible, because I didn't give it a list of URLs. Let's look at. Yes, there's our sponsors. So you can see who's there. We've got Bluehost, Mindfire, SaltStack. I just went down the sponsors page and crawled all those and just put them in. Now the Guru Labs, you'll notice, is an SSL URL. They do an implicit 301 redirect from the non-SSL to the SSL. Good for them. No one else does, but they're going to get a little bit quicker response because of it. So let's see how this goes. Not bad at all. Everyone did pretty well. UVU clearly did the best. I wonder why that is, but everyone else did pretty good. under a second for everybody. So our total time was 4 seconds. We add up all the times, and you get that number there. So this is blocking. Let's open this up. I'm going to open this, and we're going to. Okay, so now these two programs are functionally identical. This is the AnyEvented version of this one. You can see that I've added 2 lines at the top there. Use EV and use AnyEvent. Other than that, we're making the same user agent. We're opening up the same file in the same way. We're starting a timer. We're running the crawl routine. And this one's different. We start an event loop here. In this program, we chose EV for our back-end reactor. That's the thing that will generate the events that we're listening for, like timers, network activity, signals, those kinds of things. Print out the total time. The crawl routine is a little bit different, but not much. We take our user agent in. We set what's called a convar. We're going to talk at length about convars because they are tricky subjects sometimes. A condition variable you can think of as sort of a merge point, a place to stop when you invoke its receive, which is implicit here, unfortunately. This just creates an object. Just think of it that way. It doesn't do anything right now. It's just making an object with some data inside of it. There's no functionality going on. We read the links. We call CV begin, and then we start the timer just like over there, and then we get a link. Now you'll notice here I'm using the user agent in non-blocking mode, which means that I'm going to give it a callback instead of waiting for it. If I don't give it a callback, it's going to assume he's waiting for an answer, so we just better just wait. In this case, it sees that I have a callback that says, oh, okay, so we can just keep on going. So what happens is we get down to we go through the list here, through the loop. We get to this. It fires off the web request and keeps going. It does not wait for an answer. But it does register this callback to fire when the response comes back. I'm going to bump that over so you can see what's at the end here. It's not that important. I'm just printing some stuff. Maybe I should just format that. Oh, that wasn't very good. Well, idiots. There. It's just printing out the time. Okay, so let's see how well this one does. CE Perl crawl non-blocking with the same sponsors list. Okay, that took 1 second, a little bit under 2 seconds. There was some launch overhead there. Let's see and why that was. Oh, well, the reason that was is this will take slightly longer than the slowest link. In this case, it was X mission at 1.8 seconds. That's funny because yesterday when I was trying this, X mission came in at consistently the very lowest. If we run it again, it's likely that there we go. So now X mission is doing much better there. Binary Cocoa is the loser. It's 0.6 seconds. And you can see that our total time takes as long as and just with a little bit more of overhead as the very slowest one in the loop. All of these are what we did is in the order. These are coming back in the order that they finished, not in the order that we made them. So that's why it's ordered from quickest to slowest there. So this is just an example to keep in mind as we start now getting into condition variables. This is just an example of why evented systems can be very powerful. You can get a lot of stuff done without very many resources. Using my laptop, I can do some damage to some sites, overwhelming with a lot of web requests. Okay, so we've seen some of the benefits of non-blocking event-driven code. We're going to start now with condition variables. Condition variables can be a little bit off-putting. They were for me until I understood what was going on inside of them. So we're going to take the screwdriver out and open them up a little bit. Some people call them sync points or merge points. I don't know if you've used those kinds of terms in other paradigms, but I like to think of them as a Unix pipe. where you put something in at one end and something pops out at the other, except they don't block like Enix pipe does. Okay. So let's look at, we've got another example here, CV1A. This is an example of using a convar with a timer. So we start our timer. That says 3 seconds. We create a condition variable. We create a timer. After 3 seconds, we tell the timer to fire this callback, which in the callback, we take the condition variable that we made and we send the string 3 seconds to it. And then we print out the receive. So there's a send and receive side of a condition variable. So we receive that. What receive does is it actually waits. It will wait there until send. All send does is it opens up the object and it stuffs something in one of its attributes in the AE send attribute. And until there's something in there, receive will block. It will just wait. Actually doesn't block. What it does is it returns control to the event loop and it keeps checking so that your program doesn't stop. It feels like you're blocking here, but the rest of the things that might be going on are not blocking. And so that.
If you put a line right after that say, when does that happen?
Like that?
Yeah. So it does block at that point.
For your program, it feels like you're blocking. But if I had multiple timers, or if I were making multiple read requests, which I'll get to an example of later, they would not be blocking. They would that receive is passing control back to the event loop. Actually, so it's why we call it a sync point or a merge point. It allows you in your program to. It feels like you're stopping everything to wait for the answer you need. This is actually not a paradigm or a way to use AnyEvent. Except in very small cases like this. It's largely meant to illustrate how send and receive work. One sends on one side of the pipe and receive takes it off the other side of the pipe. I heard a.
Well, I was curious. So is there a version of receive that waits for all children, so to speak, kind of like
Yes.
the parallel fork manager has?
Yes, and we'll show that as well. Yep. Okay. Any questions about this? This is that was a good question, Rob. So we have our condition variable and timer. How does this work under the hood? Okay. Here's our program. So we run the timer. We create a condition variable object here. It has one attribute called AE sent. You don't need to know this in every day, but I found it very useful for me to understand why condition variables work the way they do. There's an attribute inside the object called AE sent. We create a timer. The timer goes into the event sources of the event loop. In this case, we're using AnyEvent directly. AnyEvent, built into it, is a pure Perl event loop. If you don't have one installed on your operating system like EV or modulicious IO loop or PO, whatever, it just has one built in, and it's a pretty performant event loop. So we've added a timer to the system to start counting the 3. We also add the $W as a watcher. This is where the callback is stored. Now we say we print out waiting. And now we hit that CV receive. So what this does is it says, this is what the code for receive looks like, basically. I've really trimmed it up quite a bit, but it's a little subroutine on the CV object, and it says unless this attribute is set, poll the event loop, and keep polling it until it is sent. So poll means one tick, essentially, in an event loop. It goes around the loop once, and checks all the timers. It checks all of the signals. It checks all of the I/O handles that we may have registered our intent with. And then if there's nothing there, it comes back and it says, is AE sent set yet? No? Okay, let's do it again. So this is how receive, it feels to you like it's blocking, but it's not blocking the event loop. So it's going round and round. So then here is our event loop. It goes around and around, and it's checking the event sources until that timer goes off. Eventually, the timer is going to go off. The event loop notices that, and then it runs around and checks to see were there any watchers for this event. It finds one, and the watcher says, thank you very much, and it fires its callback, which is, in this case, send. Send looks like this. It takes whatever you give it, 3 seconds, wraps it in a little anonymous array, and sets AE sent. And then it checks to see if there is a callback and runs it. If there's you can also attach callbacks to your condition variables. We did not do that here, so that second line isn't going to be run. But AE sent is now set. So it's this object it's a global. We're just using the same object here. Well, now when we get back to receive, this condition is now suddenly true, and so receive returns what was inside AE sent, which is 3 seconds. And then we can finally print it, because say was waiting for that that method to come back. And I think that is that for that slide. Okay.
How's that scoped?
Sorry. Whoops. How is what scoped?
Just that, is it only scoped to the anonymous array that you sent? Or what is visible
What context?
to the different, let me see, are there globals that are visible?
Oh, this would be shifted in. I just shortened it. This CV is the self in this thing, but I didn't have space for that. Is that helpful?
Yeah.
Yeah. This would be like my CV equals shift CV arrow, right? It's the instance of the object of the condition variable that you created earlier. This one up here, this $CV. So you just made a new object there. This is the object method. It's not a class method. Does that answer your question? Okay.
And the callback there, the
Here?
ABCD, that's not the callback that you actually set. That's an optional callback that we're not setting in this example.
Correct.
But it would be a callback for the convar itself rather than for the timer.
Yes.
So the convar could do something also that's outside of the main program. So that would be
Correct.
finishes everything you do.
Yes.
The convar callback.
At the end of the condition variable, that its callback will be fired if there is one there. So we'll get to this in more detail later, but what a lot of people do is they'll put their receive inside the callback so that they never block anywhere. Because you know that once the callback is fired, that there's something set, and so the receive will never block. So that's kind of a clever little trick, is to put that receive up inside of the condition variable's callback. We'll see an example of that later. Great questions. Anything else on that? Okay. So you can have multiple condition variables to wait for multiple things at once. Well, let's get to the next slide. Okay. So in this example, we're going to look at actually, before we do this, I'm going to oops. Okay, so here we're creating a user agent. We're going to go fetch a Google page, create one condition variable. In AnyEvent, you can use the long word AnyEvent arrow convar. Built into AnyEvent is a smaller package. It just comes with AnyEvent. You don't have to use AE. It's just it's there. It just sort of wraps some of AnyEvent and just makes things shorter. I've done that here. You don't have to do this. It doesn't help in any way. Just makes things smaller. We make a new condition variable. In this case, we have set a callback on the condition variable. Now we're going to print out making a URL. Now we're going to make our URL request, and it's a non-blocking one. We've set the subroutine to print out URL response received. Then we're going to invoke CV send, and we're going to pass in pop, which in this case is the Mojo transaction object. You don't have to worry what that is. It contains the response, essentially. And then we say sent. We print out URL requested. Now remember, nothing in the callback is fired yet. That's going to happen when the response comes back. We create another condition variable, CVT. We're gonna make a timer here, and a condition variable for a timer. I should tell you up front, this is an anti-pattern. You would not do it this way. So don't be thinking, oh, I gotta. It looks like I'm making lots of stuff. You are. This is not a good way to do it. But I'm showing you it can be done, and it's not, the end of the world kind of thing. This is something kind of a naive approach to it. We make another condition variable. We set a timer. We say we're waiting for the timer. Oh, and inside the timer, our callback for the timer, we are going to send the timer is done back to the condition variable. And now we wait for the timer, and then we wait for the URL. We don't know which one's going to take longer. Probably the timer will take longer because Google is fairly responsive. Let's just see how this works. Okay, just like we thought, we're making a request. Timer is done. Waiting for Google. Oh, I don't know. It was working before, right? Oh, there we go. That just took a long time. Oh, I guess maybe it timed out. I don't know. Well, you can see all the things that happened there. The timer finished. We're still waiting for Google. Let me change that to UVU, see if that goes a little bit better. Yeah, that's pretty good. So we can see that the CV callback fired. This is the one for our URL. It finished before the timer did. But we didn't get the response until after because of the order of how we put things together. It's a clumsy way to do things. This is the anti-pattern illustrated here. This is a little bit different with two timers, but pretend that first one is a web fetch and the second one is not. It's a timer like we had in the program. We run two timers. We create one condition variable whose AE sent is set to undef. Create another condition variable. We set a timer and a watcher for one of them, and another timer and another watcher. Now the second timer is the quicker timer. It's going to happen faster, but in this case, we're going to be polling on the first one. Now our event loop starts and it goes around and around. And after 2 seconds, it notices that this one fired. This is the event loop. This is not the convar is not doing anything. It's just running the loop. The loop says, oh, timer went off. Who was watching for that? Oh, it was you. Here you go. Thank you very much. Well, so what happens now? Anyone? What happens? What?
Just go through the loop again?
Yeah, right before it goes through the loop, because this watcher happened, its callback is going to trigger, right? Before it goes back around the loop. So that happens. The convar is set, but we're not there yet. Internally the condition variable state has changed, but we're not able to. Yeah, we can't even access that yet. So this is why this is an anti-pattern. We go around the loop again. The 3 seconds finally goes off. At the next one, we notify that watcher. This is the 3-second one. So then its AE sent changes. And immediately, so once we print this, of course, the second one is not even blocking because AE sent is already set. If you remember how that works in there, it will pull until it's set. So in this case, it doesn't pull at all. And it prints almost immediately after. So this is definitely an anti-pattern. You don't want to do it this way. There is a better way. And so we're going to look at now begin and end. Before we do that, there are three attributes inside of a condition variable. There's sent that we've been talking about. There's also a counter. And this is used to wait for multiple events. David, this is what you were asking about earlier. Is there a way to collect and collate all these events into one thing? Yes, there is, and it's with a counter. And then there's the callback that, Rob, you'd noticed earlier. It will run when send is invoked, if there's something there. OK. So this is a light example of how that one works. We will say fetch URLs. That's the name of this program here. We create our condition variable. We'll just make one condition variable. It has inside of it our three attributes. I'm showing all of them now. Then we invoke the callback method. All it does is it sets the AECB attribute to the subroutine that we gave it. It's a setter. Then we invoke begin. The only thing begin does is increments the AE counter. That's all it does, plus plus. It's very simple. Then we run our get. We make our web requests. Out the window it goes. We set the callback and the watcher. I'm not illustrating those like I've done previously. We invoke begin again. It increments the counter to 2. We make another web request. It goes out the window. We print running. Then we invoke the event loop. And now the event loop is going to go round and round, waiting for those I/O events to come back, those network I/O events that we want to know about. We've said, hey, I'm interested when this network socket has some data on it. Tell me. So we finally get, let's say it's the second one was the quicker one. We run the get callback, which is that right there. Say URL2 is done. And then we invoke CVEnd. CVEnd does one thing. It does two things, but in most cases it does one thing, and that is it decrements the counter. That's all, minus minus. We loop around until the second all the events we're waiting for have happened. A URL1 response comes back. We invoke a get callback, which is that one up there. We invoke CVEnd, which decrements the counter. When the counter hits 0, it runs CVSend on the condition variable. And that's how you collate multiple events into one. It lets you, it sort of ands all of your events together without making them block. At this point,
Is the counter number be used as an ID at some point?
Sorry?
Is the counter number useful?
Nope. No, you wouldn't ever see it.
Yeah.
Outside of this presentation, you will never see it anywhere. It's just an illustration of how it works. So yeah, it's an internal attribute that's just plus plus and minus minus. That's all it is. Yeah, it's just a really simple counter. When it gets to 0, we invoke CVSend, which sets sent to true because we don't have we're not sending an actual. There's no value to send. It's not meaningful in this case. Send it to true, and then the callback gets to fire here, and so we say all URLs are done. That is pretty much it for condition variables. Does anybody have any questions more about condition variables?
Under the hood, how is the event loop happening in parallel? Is it threads working? Some other thing I've never heard of? How are we getting parallelism under the hood?
It's a good question. We can.
It isn't really the wrong question.
No. I think it's pull. Nope. Maybe it's loop. Yes. Sub 1.
Well, if one of the callbacks blocked, wouldn't that? Are you really parallel?
Well, that's why you don't want to block in your
Yeah,
callbacks.
right, 'cause it's not really parallel, right?
It's not threads.
It's not threads.
It's not forks. I'm looking for.
That's why it's so hard to do the memory.
One event. Here we go. This is the built-in AnyEvent event loop right here. It's called one event. This is the same as one tick in other event loops, or there's a lot of names for it. We look at the timers, and we do all the timers first. If there are no timers that need to be dealt with, we pull for the I/O events. And so this is actually using a select on the file descriptor. So for if you have about 1,000 or fewer descriptors, this will be fairly performant. If you have more than that, you'd want to use an actual event loop backend like libev or libuv that uses KQ or some other higher performant
So
loop.
the parallelism then is being handled completely outside of Perl.
Yes.
In that
It's native to your operating
kernel,
systems.
It's either the Linux kernel or
Yep.
one of those native systems.
Yep. Does that help?
Yeah, that's
Okay.
exactly what I was wrapping my head around.
Good question. Any other questions on that?
I'm backing up.
Yeah.
Mine also says something like, when you call get on the
Mhm.
first example,
Mm-hmm.
it seems like you passed the callback to that. But maybe I,
On this example or another example that I've done?
yeah, so the callback, is that any event calling the callback? I mean, how is that?
No. This is a Mojo user agent. Mojo user agent is a supports non-blocking I/O, which means it typically accepts a callback of some kind to run. So when it gets a response back from the network, you could use other user agents. It doesn't have to be that one. It's just something that's part of, in terms of network I/O, that's generally how it's done. There's disk I/O, which isn't very different from that, how it looks. I'm not fully addressing your question.
No, you did. For
Okay.
some reason, I've done gets before, and then I was like, wait a minute. But I wasn't doing anything.
Yeah. Okay. Well, we got through the hardest part here. The condition variables are very tricky. The other primitives, I wish there were a faster way to get through these slides. The other primitives, are we've looked at a little bit at network I/O. There's also disk I/O. There's a module out there called IO::AIO, which was written by the same author, Mark Lehman, and it does truly asynchronous disk reads and writes. It is an amazing piece of work. If you ever had to stat or read thousands of files, you would have cried for joy had you discovered IO::AIO before that. It can do all of those things in parallel without waiting for your disk, because disks inherently have to block. There's no way to say, oh, just get back to me, because they're like, no, I'm doing the seek right now. You know, it's coming. So timers we've already looked at. Signals we've already looked at. Idle, this is an example of network I/O. This is what disk I/O might look like. There's an AnyEvent IO object. You give it a file handle. That would probably be a non-blocking file handle. It's a read. We're going to wait for something to read, and then we stuff it into a variable and send it, and then we wait to the end. So that's disk I/O. Signals we've already looked at. Oh, we didn't actually look at signals in the AnyEvent way. This is the way I showed you earlier. And this is the AnyEvent equivalent. We just set a signal, and it will. This is actually a lot more responsive, because the problem with this one is when you sleep is not reentrant on most Linuxes, unless you use a special kind of sleep. In Perl, it's typically not reentrant, which means if we are in the middle of this and our signal handle fires, we lose the loop. We jump out. And this is not. It's fully reentrant. All the timers and everything. So AnyEvent are great for simple applications. I wouldn't ever recommend them for large applications. They are. It's like working in C. You're like, oh, there's so many little fiddly things you've got to get right. But the good news is there are hundreds of really quality CPAN modules. There's hundreds of also really crappy ones built on AnyEvent. So you would use. I would recommend if higher level abstractions like promises, futures, or IO delay or something like that. If you really want to do clean event-driven programming, but under the hood, all of these AnyEvent will work with all of these really well. I think that is it. Any other last questions? Thank you.